Welcome to the Evolution Show. I'm Johan Landgren. I hope you're great. Today I continue my conversation with Anders Forslund, the CEO and founder of electric plane pioneer Heart Aerospace. In part 1 last week, we talked about the recent unveil of Heart Aerospace plans for the world's first 30-seater electric airplane, the ES-30, and a new factory where they will build it, as well as new purchase orders from Air Canada. Today, I hope we can answer some of the most common questions I've seen since the ES-30 electric plane was announced, and talk about the more technical aspects of the plane. And finally, I hope you liked the episode, and if you do, don't forget, give it a thumbs up and consider subscribing. As always, stay ahead of the curve and stay electric. This is the Evolution Show. Okay, welcome back, Anders Forslund. Part 2 of our conversation about the news on Heart Aerospace.
Yeah, I'm excited to be back.
So, in the previous episode, we covered some of the most exciting parts from the Heart Aerospace Hangar Day that you recently had. And I was invited as an investor in the company, and we talked about the unveil of the new electric Heart ES-30 plane. That now is being developed. It's at Säve Airport, and also you unveiled, for example, a new factory that you will build there. And of course, there were a lot of investors there, and there were new orders also announced from Air Canada. But in this episode, I thought we could cover some of the most common questions that I have encountered in the social media recently, and especially when it comes to technical details of the plane and so on. And so people, before we talk a little bit about different weather conditions and so on, how that affects the range, people are obviously asking that all the time because they compare with electric vehicles and so on. Starting off just a little bit about the turbogenerators, just explain how they work, because it's a fairly new thing. And when I read about turbogenerators, I saw that Rolls-Royce are developing them, and they are also, I think, will be introduced with fuel cell technology later on and so on, because obviously you can run turbogenerators with any kind of power. If you have so can you explain turbogenerators and why you went with them?
Yes. So I mean, first of all, I would say that the concept is not new. In fact, in every sort of commercial jet aircraft that are out there that's flying in commercial traffic that's over a certain size, there's something called an auxiliary power unit in the back. So turbogenerators have existed for a very long time in aircraft, and they're anyway, you hear them when you're sitting on an aircraft on the runway. There's the sound that you hear while waiting for the aircraft to start, but it's running the air conditioning. And they're there as an auxiliary power system. That means that they're not used for propulsion, but they're used to drive other parts of the aircraft, essentially because you don't have large batteries on a regular aircraft, and you want to have the redundancy. Even though you have small generators on board the jets, inside of the jet engines, you also have that redundancy, and you have that auxiliary power system that you can run without the jet engines being on. Now, the auxiliary power system generally also works, it has hydraulic connectors and all of that stuff because it feeds the hydraulic systems and other things. But a turbogenerator is like really a piece of technology that's only used to spin a generator. So you have a turbine spinning a generator. And the way they are generally being built is not to use, and you could take an APU from a much larger aircraft, say from a Boeing 787 or something like that, and you could put that in our aircraft, and you could fly with that. But then that carries unnecessary complexity because it also deals with like hydraulic systems and all that stuff. So the way that you really do it is you take a helicopter turboshaft engine and you put a generator on that, and that's what several companies are developing. Some are doing actually clean sheet designs only for a turbogenerator, but it's not like some new inventions. It's something that's been around for a very long time, and I think the innovation that's happening there is to making them even more efficient and light. So that's why it's not. It might sound that we're putting a lot of never been dones on this aircraft, but it's actually building on a history and legacy where this is very, very commonplace.
Yeah. Yeah, and I think I should clarify what I meant. I meant the electric motor combination with the turbine. That's probably a little bit more new.
For sure.
On airplanes. So that's what I meant. But
no, but I think
good that you cleared that out.
Yeah, I think so. So running, I mean, the difference.
I asked the wrong question, but doesn't matter.
The difference here is that the turbo generator is not feeding the auxiliary systems; it's feeding the propulsion, and it's not really being. Well, everything is running on the same system more or less, or the batteries have different voltages and feeding. We have all of the redundancies, but we don't need the turbo generator to create the redundancies. We need them. We need it to increase the cruise segment of flight. And the reason we have two is also actually for a redundancy purpose, because we have to account for the possibility of a failure of one of the turbo generators.
Okay. Yeah. But also we have to touch upon, we mentioned it in the previous episode, but talking about range, but how does different, for example, weather condition affect the range? When we talk about 200 kilometer range just going on batteries, people are asking now in different forums and so on, yeah, that's fine, but when it's 10, 15 below Celsius, up in the air, will it still be 200 kilometers and so on? So how does different weather conditions affect the range? Have you calculated on kind of average range or some optimum range, or how do you come up with this figure of 200 kilometers range?
Well, one of the most common misconceptions is about batteries, that I think that people are saying, well, isn't it like big temperature differences in flying planes, much more so than with a car? And that's true, but there is actually aircraft are all flying in scheduled service. So, the reason that your Tesla might have diminished range is when you haven't preheated the battery. So if you preheat the battery and make sure that it has a correct temperature before you take off, you can actually keep that battery temperature throughout the duration of your journey. And it's exactly the same thing with aircraft. So we're never going to take off with batteries that are the same temperature as the temperature outside if it's too cold or too hot. So, the preconditioning of batteries is key, and that's how we can guarantee both the uniform performance of this aircraft and also, the wear, the cycle life of the batteries. The 400 kilometers is calculated using, sort of in average weather conditions. So sometimes there'll be headwinds, sometimes there'll be tailwinds, but we also have some safety factors there as well. So, for instance, we're not using a battery that is 100%, charged up to 100%. So we're putting some of those things in there, but obviously that's also where it makes it interesting that we have the turbo generator. If there's like a large headwind, that we're not being grounded because of that.
Yeah, and when you're starting off an airplane from the ground, obviously that takes a lot of energy. But I assume that you will use the batteries for takeoffs in any case, because of the local pollutions and the sound and so on, and with the positive aspects of that having on the airport and the regional area, the area in the surrounding the airport. Yeah. So is that what you're going to do?
Yeah, that's correct. So at takeoff and landing, we're not engaging the turbo generator at all. And this is because of local pollution. It's about sound. It's about all of these things. So it's used in the cruise segment. So the reason of that is that we want people to be able to live close to airports. We want to make airports an integrated part of our communities. And we want to open up air travel. One of the most exciting thing about electric planes is not only is it like half the noise of a similarly sized turboprop, it's much more pleasant noise, and it's also, the taxi phase is almost silent and very efficient, because sort of a jet engine can only run at one operating condition, and that means that when you're taxiing, you essentially have to waste a lot of energy, and the only way to get rid of it is to tilt the pitch of the propellers, essentially making them something that generates noise instead of thrust. So this is like, we've tested with our propulsion rig, the first one, running it at taxi, like and it's nothing. It's like you can stand a few 10, 20 meters from it and have a normal conversation and don't really think about it, right? So it's really, really quiet.
Yeah. And talking a little bit about batteries, I mean, let's say that in 4 years or something, there will be some big improvement, at least gradual improvement that would increase potentially the range of the plane with, let's say, 20%, for example. Is it possible for you to use that battery in that plane that comes out in 2028, or do you have to go back in, look at the application and so on?
So that, the plane is just a vehicle for the battery technology, and the plane has a much longer lifespan than the batteries. So essentially, when you're having a plane has a service life of 10 to 20 years, and even the motors we're designing with that service life. Whereas the batteries will last for maybe 2,000 cycles, which could mean that you have to replace them every year. So obviously, we have to, whenever we replace the battery technology, we have to do some additional flight tests. We need to get, additions to our amendment to our type certificate. So it's not going to be, it's going to be a little bit of a lag there, but that's the entire idea. Is that, and how much does it change? Well, actually, you're bringing up like a 20% increase, and it's proportional when it comes to the physical range you can fly. But since the segment of the batteries, the part of the batteries that is still being left for reserves, just to have that power, if we have to do a go around, for instance, that's stationary, or that's the same. So actually, you get more than 20% of a range increase for this battery energy density increase.
Yeah. And something that I think people tend to forget when you talk about the range and so on with the plane is that even if you go by batteries and you combine it with using the turbogenerators, using some form of jet fuel, you would still, if you go 400 kilometers, as you mentioned, you would halve the emissions just by doing that. Yeah. So it's a huge improvement from today.
Yeah. And that's also important because this turbogenerator will operate on SAF, with Sustainable Aviation Fuel for biofuels, and the problem with SAF is that it's expensive. It's like 4 times as expensive. But so if you have the consumption of it, it makes really not just a great environmental benefit, but also an economic one. Most of the time, we're not even going to use the fuel. So it's just there for reserves, just like a fuel tank in the trunk of your car.
Yeah, and just to touch upon something that I know people have also raised on the internet is that sustainable aviation fuel sounds good, but it's actually 3 or 4 times more expensive. So how would that change the calculus or the total cost of the flight?
Yeah.
So have you looked at that?
Yeah, I mean, first of all, it is if you use half as much for a 400-kilometer route, that's half the price as well. For the shorter routes, the 200-kilometer routes, you're not using anything at all. So you're just paying to have it there, and you're just paying for it once. And also, even for 400-kilometer routes, obviously the price of fuel becomes that becomes an increasingly portion of the costs as ranges increase, right? So if you're flying long haul, then it becomes really punishing to pay 4x. But if you're flying short haul, it's not that big of a deal, right? So it's more about making sure that the low maintenance that we have on our systems, on our motors, all of that stuff. That's the main economic proposition.
Yes, and that's good that you mentioned, because we can just finish off by talking about electric motors, the benefits with electric motors, because you have, as you said, huge costs today related to the maintenance of the planes, and I don't think people really appreciate how big that cost is, and how big of a difference it is for you as a for aviation, for aviators and so on, airlines to save costs.
Yeah, I mean, I think this is one of the first things that drew me to this. Obviously I worked with jet engines when I did my PhD. It's so expensive. It takes so long time to develop jet engines. There are only a few companies that have the capability to actually do it. They measure, the design cycle times in decades. Electric Motors, we built one, right? We actually have our 2nd generation here right now, together with a supplier that's Face, which is awesome. But it's like one moving part. It's no fuels, there's no temperatures, there's no combustion. There's, all the force is being exerted electromechanically, which is really like great for wear. It's all, controlled digitally. It's just it's essentially, or it's not just essentially, it's really the same technology that's on your consumer drone. Like it's the same, it's just, you just scale it up and it's the same thing. So that's why you get, it's at least a factor 20 less expensive. And it's also virtually maintenance free. So the aircraft that even the motors that we now have on the ITF, we put the bearings in that are actually last for the service life of the aircraft. Of course, you still need some motor inspection, but it drastically reduces by probably around 2 orders of magnitude the amount of money that airlines have to spend on motor maintenance or engine maintenance. Obviously, we still have the 2 turbogenerators, so that's been something that we've added, and they have some of that complexity of the jet engines, but then they're not being used as often, right? And they're only dimensioned for the cruise segment of the flight. And at the same time, we've actually grown from 19 passengers to 30. So we've increased the sort of revenue that we're making per flight with about 57% or so, just based on passenger count.
The new design looks really great, but many wonder why you have designed the plane with so-called semi-cantilevered wings, or using external support for the wings.
So the cantilever wing. So first of all, the ES-30, let's be clear, it's not a very fast flying aircraft. So cantilever wings have existed for long. And if you go back to looking both at old aircraft and some new aircraft as well, they have this because it becomes very structurally efficient. The reason that some airlines or some aircraft don't have it is because they're going faster and it's generating drag, but it's not that much of an issue if you're flying at the speeds we're flying of about 140 to 180 knots. So at the same time, you're saving a lot of structural weight. So essentially, our aircraft carries a lot of batteries, and by adding this strut, you're creating a load path which is much more efficient. So that's some of the reasons about that. It's also about crash worthiness. Making sure that the strut sort of supports the wing in the event of a hard landing. So, which is, it makes all the sense in the world. You can actually look at aircraft. NASA had a concept where they studied the strut as a way to build a much more high aspect ratio wing. We've also seen it in new aircraft like the Cessna Sky Courier, which is a new aircraft being developed, but that also carries a strut. So, the only thing I heard about the strut, it's kind of like, from a personal point of view, it's kind of like some people, especially in the industry, they have opinions about it and they think it looks old-fashioned. But I'm like, that's not a good, argument. So I think that everything goes in cycles, and I think that the addition of the strut from just a purely aesthetic sense, I think it has made our aircraft look more original and more iconic. And that's not the reasons we put it there, but I know that some people in the industry, they don't want to have it because they think it doesn't look a certain way. We kind of think that it looks cool.
Yeah, and you also have to be practical.
Yeah.
I totally understand that. I mean, if you have batteries, that's the main thing. You want to go as far as possible, and so on. So for me, I mean,
it's another thing also with the landing gears that actually we have this big belly fairing and we have the landing gear there. And one of the problems we had with ES-19 was that the wheelbase was very narrow, but now we can actually expand the wheelbase and have a pretty simple landing gear, which is something that should not be underestimated in the design of an aircraft. A simple landing gear means low maintenance and low development costs and all of that stuff. So, and it also creates, actually, with the high belly fairing, the strut actually creates an escape where you can actually, you have the emergency exit just just by the strut. So there's actually a step on the strut. So if you open up the emergency exit door just by the strut, you can actually go out and take a step onto the fairing/strut, which also allows you to get out of the plane without having, some inflatable slider or something like that. So
yeah, and talking about the belly of the plane and this part of the plane, I mean, it's obviously also a space where you can put in the fuel, the batteries. I mean, so I guess that also was part of it. You obviously had to fit in it, and then of course you free up the space in the nacelles. In the ES-19 you talked about having the batteries in the nacelle. Yeah. Now you can just focus on having the engines there, right, or the motors, electric motors.
Yeah, I think there's been two design philosophies that have kind of been clashing against each other. I think the first idea with the ES-19 was that we isolate the innovation. Everything that's new about this aircraft goes inside of the nacelle. We have the charging, we have the electrical motors, the power electronics, and also the batteries. And that's also what we rolled out at our Series A, a demonstrator of this, and showing that, look at this, in this nacelle lies everything that's new, and we've already demonstrated that. Now it's just to stick it onto an aircraft. So that was like the design philosophy of isolation or something like that. But there's another paradigm which I think is much more prudent. What we learned in actually building this nacelle is that it's more about, it's what's called axiomatic design, is to separate functionalities. So essentially, the problem with having everything in the nacelle not only carries the motor, it carries the pitch actuation mechanisms on the old aircraft, on both aircraft, but the batteries on the old aircraft, and also the folding mechanisms for the flaps. So this becomes this nest, this very integrated systems. And if you're changing the design of one of these things, if you're changing your pack dimensions, you get all of these interaction effects, and you have to redesign the whole thing. So it's much better the design we have now, where we have like batteries in one place. We have the nacelles much smaller, and they just carry the motors and power electronics. We have the actuators for or the flight controls for the flaps, separated for those. So this means that as our teams are working, they don't get to these interaction hell where they're like, I'm making an update. Oh, we're changing the motor design. Okay, what happens to the battery pack? And vice versa. And it also provides them more flexibility for the battery packs, not only in the design phase, but also as we upgrade to new chemistries. We don't have to redesign nacelles and motors. We just have it there. But perhaps most importantly, for maintenance and charging, everything is down there. Everything is easily accessible. It's easier to plug in the charger. So and then there's a bunch of flight dynamics reasons. Where do we keep the weight? Where do we keep the moments of inertia and all that stuff? So it makes all the sense in the world.
Yeah, and I have to, since you mentioned it, people may wonder how long would it take approximately to charge the plane after you have been,
I mean, our requirement is to do it less than 30 minutes. So, and there's a lot of cell chemistries that can achieve that. But we will announce even more about this when we're going out and discussing our cell chemistry. But that's 30 minutes or less.
Yeah. Yeah, we can talk a lot, and we have covered a lot, I think. I would love to talk more at another time about different technical details and things that you will develop over time. And for people who don't know, behind you, we're actually sitting in the hangar where it's kind of a skeleton of the plane. And I have pictures for people, and we'll see it also. So, but it's fantastic to follow and so inspiring, hopeful for the future, exactly what we need. And it's going to be exciting to follow up what you're doing. And again, thank you so much, Anders, for taking your time, and good luck with your next meetings today.
Thank you. I am already late for the next one. So
that was all for today, folks. I hope you liked the episode. I'm curious to know what you think about the new ES-30 plane and what challenges and opportunities you see with electric planes going forward. Share your thoughts below. Up next is an inspiring talk with the 5th generation oceanic shipper from Norway, now the CEO and founder of a Norwegian company that wants to electrify regional container shipping in Europe. So stick around for that. And before you go, if you like the Evolution Show, give it a thumbs up and consider subscribing. I hope to see you next week.